Okay, now let's suppose that our mass is attached to this beam, and we want to rotate this beam at 2 revolutions per second. Okay, and I don't even know how to do this, but okay, let's see if I can get this up here. And okay, maybe I move through 1 revolution in ½ second. So how much kinetic energy did this beam have at that speed? Let's assume that the beam has a mass of 100 grams. Actually, I think that's a little closer to 200, but that's okay. Okay, so let's also assume, and it's not quite true, it's only 30 centimeters from here to here, but let's assume this is 40 centimeters. So our original 100-gram mass was out here at the 40 centimeter position. Okay, it had the kinetic energy that we've calculated. Now we want to get the kinetic energy of the beam as it's moving at 2 revolutions per second. Assume we have 100 grams here and that this is 40 centimeters from here to here. Now we want to partition the interval from 0 to 40 centimeters. And we want a typical interval of that partition to be some short increment out here at some distance, which we'll call r star. How much of the mass is in that short interval if the interval has length delta r? Okay, well, we just take delta r divided by 40 centimeters and multiply that by the mass of, let's say, this half of the beam. Or alternatively, we can assume that delta r means all the mass at distance r star from the center within this short interval about r star. So if r star is, let's say, just this far, 1 hand span, and we do a very short interval out here with r star somewhere within that interval, then we have another interval over here on this side of the same size, and those 2 intervals of the object correspond to that interval of distance from the center. Okay, so for this far from the center, we could be here or we could be here. If our interval has this length, then we have an interval of that length here and an interval of that length here. How would we express the mass within that interval? Well, you can think about it. It's a simple proportion. It's delta r over 40 centimeters times our total mass. So make sure you understand why. Make sure you think that through. Here's a picture of our 2 intervals. Here's all the points at or close to distance r star within an interval of the width that we see here. So what portion of the total length is this plus this? Well, the same as the proportion of this divided by the 40 centimeters. Okay, just one of these divided by 40 centimeters is the same as the width of 2 of these divided by 80 centimeters. And that's the proportion of the 100 grams that lies within that distance of the center. So what's its kinetic energy at 2 radians per second? Well, let's just use omega for the angular velocity, so we can do this for any angular velocity. The speed at distance r star is omega times r star. Now make sure you understand why that is in terms of the way this was reasoned out. That's a formula, but make sure you understand what that means in terms of the definition of pi and definition of a radian. Okay? It follows then that the kinetic energy is 1/2 mv squared, where m is the mass within this small interval at this distance, which is delta r over 40 centimeters times 100 grams, times a half, because kinetic energy formula has half in it, times the square of omega r star. That's how much mass, this is how much mass, this is the kinetic energy of that mass. Well, if we sum all of these contributions up, and that's too small to read. It just says 1/2 delta R over 40 centimeters times 100 grams times omega R star squared. Now I had omega squared R star squared, but I'm going to use parentheses just in case you can read that. A little easier to distinguish a star from a square if I have the square out here. We sum up all those kinetic energy contributions for all the little delta R increments. And then we take the limit as our delta R approaches 0. We get more and more of these. We get closer and closer to the actual kinetic energy. And our final kinetic energy is the integral from 0 to 40 centimeters, because we partitioned R from 0 to 40 centimeters, of, well, the expression that we get from here. Now, we didn't complete this, and I'm not going to complete it now, but we will be talking more about it. Straightforward derivation of the integral that gives us the kinetic energy of that rotating object. Now, we're going to generalize this. We're going to look at other ways of doing this. And we're going to define something called moment of inertia, and show that the kinetic energy formula can be expressed very easily in terms of the moment of inertia and the angular velocity. The first thing we want to understand is how the position of the mass, how the position of some given mass on this beam affects the kinetic energy of that mass, and the fact that the effect is highly nonlinear. It goes as, not highly nonlinear, but it's certainly nonlinear. It goes as a square of the distance, for reasons that I hope we've seen.